Okay, hi everybody. I'm going to be talking about advanced modeling for the HIT-SI experiment, a paper we're about to submit with my co-authors Tom Benedette, Kyle Morgan, Chris Hansen, and Tom Jarbo. And this is a video abstract to sort of give people an idea what it's about. The outline is, I'm going to talk about briefly what is MHD and why is it useful. If you're a plasma physicist, you're probably quite convinced on this point already. I will give a brief review of the HIT-SI experiment here at the University of Washington. If you've seen my other videos, they also contain brief HIT-SI reviews. And if you really want to understand the experiment, you probably need to dive into the literature a bit. But I'll show you so you can have some context for the cool results I show later. I'm going to talk about what this work does, which is the implementation of a two-temperature Hall-MHD model in both the Nimrod and the SciTech codes. I put the new model into the SciTech code, and my co-author Kyle Morgan implements it in the Nimrod code. And then I'm just going to show some highlights from the paper showing sort of new things with this more advanced model. So just to motivate MHD, I'm going to show this cool video from NASA where we're going to see a solar flare develop and sort of shoot outwards. And then a giant region of magnetic activity is going to develop right in this region. And sort of the motivation I'm trying to bring here is that plasmas are highly nonlinear, highly multi-scale, extremely dynamical over potentially very, very large regions. And so this sort of begs the question of, we want a complicated, complex model to simulate these plasmas. But we also can't simulate the whole sun because this would just take way too long to compute all the things we're interested in. And so we have to balance how complex a model are we going to use to simulate the plasma and how fast can we actually do it. And MHD is computationally efficient for certain types of plasmas, and for speed, typically the electrons and ions in the plasma are often considered as a single conducting fluid with a single set of evolution equations. And this is sort of contrasted with for instance, a two-fluid MHD, which would treat the electrons and ions separately in their own evolution equations, which are nonlinearly coupled between them. And so-called Hall-MHD introduces Hall terms that mimic two-fluid effects. So in other words, you still have a single set of single-fluid equations, but you've included new terms in there to mimic the effects if you were evolving a set of two-fluid equations. And these two-fluid effects we think are important for HIT-SI because it turns out that two-fluid effects are important between the ion inertial scale and the electron inertial scale. And on HIT-SI, the ion inertial scale is about 8 centimeters, and the electron inertial scale is less than a centimeter. And so in this sort of few centimeters spatial scale range, we expect these two fluid effects to be important for the plasma dynamics. And in fact, numerical work, for instance, Jian Akjai's dissertation showed that indeed when you put these Hall terms into the MHD models we use to simulate HIT-SI, a validation with experiment improves. So we have a good theoretical and numerical justification for why we want Hall-MHD to validate with the experiment. So let's briefly go over what the two-temperature Hall-MHD model is, and then I'll show you sort of a brief what HIT-SI looks like. Experimental HIT-SI measurements indicate the ions are 2 to 3 times hotter than the electrons. What this means is that if you're evolving a single temperature evolution equation, it means you're sort of missing some of the dynamics in the plasma, which experimentally are leading to the ions heating 2 to 3 times hotter than the electrons. And so we want to this basically motivates an MHD model where the electron and ion temperature evolutions are separate so that we can model and better validate with the experiment and basically see that the ions in the simulation are hotter than the ions in electrons in the simulation. And so we implement a two-temperature Hall-MHD model. I'll show you in a second. New terms are in red. This will basically still be a single fluid set of evolution equations, but we've split just the temperature evolution into an ion temperature evolution equation and one for the electron temperature. And just for completeness, I'll show it briefly. We have a continuity equation, we have conservation and momentum equation, we have two evolution equations for the temperatures, for ion temperature and for electron temperature. We have some Maxwell's equations, and then we have an Ohm's law for the electric field. And just to mention, these last three terms in the Ohm's law are the so-called Hall terms. So I won't talk much more about this model. If you're interested in what exactly the closures we're using or what heating terms we're putting where, please take a look at the paper. I'm going to go on, describe HIT-SI, and then show you some results. So what is the HIT-SI experiment? It's a spheromac here at the University of Washington studying plasma self-organization. HIT-SI consists of an axisymmetric main chamber and two injectors mounted on each end. The injectors X and Y. And here you're actually looking at a vertical slice down from the top. If you want to see the full volume, you can see the transparent gray here. So it actually wraps all the way around. And on these injectors, there are circuits which apply a voltage and an axial flux. And these circuits, these waveforms are oscillated in the tens of kilohertz. And what happens during an experimental shot is we turn on the injectors. These injector fields turn on, enter the main volume. They self-organize into this spheromac plasma in rainbow. And then during the course of the discharge, the injector fields in gray sort of perturb and sustain this axisymmetric spheromac plasma. And that's sort of the basic physics of what's going on in the HIT-SI experiment. I also wanted to mention that in the next slide, we're going to look at the same cross-section here from the top, and we're going to look at what's the ion temperatures in that cross-section. So I just want you to have a mental picture of what this cross-section looks like before we go on. So it turns out that the two temperature models indicate significantly increased ion temperatures compared to the single temperature. So here we see like 45 to 50 eV ions. And in fact, what you're looking at here is the injector is sloshing plasma back and forth during an injector period. And the plasma in the center is sort of getting jostled and perturbed as the injectors go on. And so this sort of gives you a sense of how dynamic the plasma is in HIT-SI. Importantly, the single temperature model only sees ion temperatures that are something like 15 to 20 eV, and we see ion temperatures that are up to 50 eV, and in fact volume averaged ion temperatures which are something like 20 to 30 eV. And that actually is a good number because we have experimental HIT-SI measurements through ion Doppler spectroscopy that show that we have ions about 20 to 30 eV on the experiment, and Thomson scattering measurements and Langmuir probe measurements indicate that electrons are about 10 eV on the experiment. And this is in qualitative agreement with, the simulations are in qualitative agreement with the experiment now. So this is an immediate result showing we can better validate with the experiment. So we're quite happy with this. What we're going to do in the next slide is we're going to just look at this cross-section here. We're going to chop off the injectors, and we're going to look at what the magnetic field lines look like in a Poincare plot, or sometimes called a puncture plot. And what that is going to show is that we have these low-density, high-power simulations, which see these like filaments form, and actually then get some closed flux forming sort of near the magnetic axis. It's going to jostle around a bit. It forms some cool structures, some magnetic islands form here. And because we have these closed flux surfaces, we see higher temperatures, we have confined pressure, again jostling around, and then it gets destroyed. And then we have some filaments form again, and it's going to reform some closed flux in the center again. And once again, this will repeat. It will get jostled around for a bit, and then it will get destroyed. And this is cool behavior. We typically don't see this until we get current gains of something like 5 in the simulations. And importantly, this sort of motivates a low-density, high-power regime for the experiment, where we can get closed flux and formation, and also these refluxing events where closed flux lasts something like 1 or 2 injector periods, or 100 microseconds or so. So this was a really cool result, and so it further motivates the direction of the experiment. So just to conclude, we've implemented these 2-temperature Hall-MHD models in our 2 codes, SciTet and Nimrod. We have 2-temperature results, which indicate both higher average temperatures for the ions and electrons, and it turns out, I didn't show this, but higher toroidal currents than the single temperature model. We also have improved qualitative agreement with experimental measurements, including with ion Doppler spectroscopy, Thomson scattering, and so on. And we also are able to do calculation of power flows and heating in Hitto-size simulations, and this sort of leads to new insights about the dynamics, in particular, why are the ions 2 to 3 times hotter than the electrons? I didn't show any results from this here, but please take a look at the paper if you're interested. And last sort of cool highlight is these low-density, high-power simulations in 2-temperature SciTet, which indicate a high-performance regime where we start to see these refluxing events. And because we have these the sort of periods of closed flux, we see higher average temperatures and sort of the associated heating with the axisymmetry. So thank you very much for listening, and please take a look at the paper if you're interested. Thank you.